Every piece of gold jewelry on Earth was forged in a cataclysmic collision between two dead stars, billions of years before our planet even existed. A kilonova occurs when two neutron stars, the ultradense remnants of collapsed massive stars, collide and merge together. Neutron stars are so dense that a single teaspoon of their material would weigh billions of tons on Earth. When two neutron stars orbit each other closely, they gradually spiral inward, losing energy through gravitational waves. This inward spiral can continue for billions of years before the two objects finally collide in a catastrophic merger. In the final moments before collision, the neutron stars whip around each other hundreds of times per second. The collision releases an amount of energy that briefly outshines an entire galaxy of billions of stars. In 2017, scientists detected the first confirmed kilonova event, designated GW170817, using gravitational wave detectors. The LIGO and Virgo observatories detected ripples in spacetime itself, caused by the violent collision of the two neutron stars. Just seconds later, space telescopes detected a burst of gamma rays coming from the exact same location in the sky. This marked the first time scientists observed the same cosmic event using both gravitational waves and traditional light. Astronomers around the world raced to point their telescopes at the location, racing to capture the fading afterglow. The resulting kilonova was observed across the entire electromagnetic spectrum, from gamma rays to radio waves. This single event provided more scientific data than decades of previous theoretical speculation about neutron star mergers. Scientists confirmed that kilonovae are the primary cosmic source of many of the universe's heaviest elements. This includes gold, platinum, uranium, and other elements heavier than iron on the periodic table. Elements lighter than iron are typically forged inside the cores of ordinary stars through nuclear fusion. But fusing elements heavier than iron requires so much energy that it cannot happen through normal stellar processes. Only extreme events like neutron star collisions provide enough energy and free neutrons to create these heavy elements. This process is known as rapid neutron capture, or the R process, where atomic nuclei quickly absorb multiple neutrons. The neutron-rich material ejected during the collision decays radioactively, producing the glowing light of the kilonova itself. Scientists estimate a single neutron star merger can produce enough gold to equal several times the mass of the Earth. This finally solved a long-standing mystery about where the gold, platinum, and silver found on Earth originally came from. Previously, scientists believed supernovae explosions were the primary source of heavy elements in the universe. The 2017 kilonova observation revealed that neutron star mergers, not supernovae, may be the dominant source instead. Every atom of gold and wedding rings, electronics, and jewelry originated from one of these ancient cosmic collisions. These collisions likely occurred in distant galaxies long before our solar system formed, scattering heavy elements into space. Over billions of years, this material eventually became incorporated into the gas clouds that formed our sun and planets. This means the gold in your jewelry is potentially older than our entire solar system itself. The kilonova event also produced a short gamma ray burst, one of the most energetic explosions known in the universe. Short gamma ray bursts had long been suspected to originate from neutron star mergers, but lacked direct confirmation. The 2017 event provided definitive proof, linking gravitational waves, gamma ray bursts, and kilonovae together conclusively. This discovery opened an entirely new field called multi-messenger astronomy, combining different types of cosmic signals. Scientists can now study cosmic events using gravitational waves, light, and particles simultaneously for deeper understanding. This approach has been compared to gaining new senses for observing the universe beyond just light alone. Gravitational wave detectors like LIGO work by measuring incredibly tiny distortions in the fabric of space itself. These distortions are so small that detecting them requires measuring changes smaller than the width of a proton. Since the first kilonova detection, scientists have identified additional gravitational wave events from similar mergers. Each new detection adds valuable data, refining scientific understanding of how frequently these cosmic collisions occur. Kilonovae are believed to occur relatively rarely, perhaps only once every 10,000 years within a typical galaxy. Despite this rarity, the cumulative effect across billions of galaxies over cosmic history explains the abundance of heavy elements. Future gravitational wave observatories are being designed with even greater sensitivity to detect more distant kilonova events. These improvements could allow scientists to observe kilonovae throughout a much larger portion of the observable universe. The discovery of kilonovae fundamentally connects the jewelry we wear today to some of the most violent events in cosmic history. The next time you see a gold ring or a platinum watch, remember that its atoms were forged not on Earth, but in the fiery collision of two dead stars, flung across the universe long before our world was ever born.